Hello, everyone. Good evening, good afternoon, good morning, depending on whichever part of the world you're joining us from. Thanks for joining the 40th meetup of Kaggle Days Meetup Delhi NCR. It's a long journey now. And today we are very glad to host Aishik. He's a Kaggle competitions master, and he would be talking about introduction to clip model and a lot of details around that. So we hope that this event becomes useful for you. Over to you, Aishik. Like you can start sharing your screen and start the presentation along with a short intro before we uh,
Okay, yeah.
dive deep.
So, hey everyone. I am Aishik Rakshit. I am currently a senior of EEE at IIT Guwahati. And as Aaron mentioned, I am a Kaggle Combinations Master. So today, we'll be talking about the clip model. And let me share my presentation. Yeah. So, could you confirm if my screen is visible?
Yes, Aishik, it's visible.
Yeah. Thanks. Yeah, so talking about the clip model was released by OpenAI, and it's like a part of the paper learning transferable visual models from natural language supervision. And today we'll be like talking about the various innovations and gains that we have achieved with the model. So CLIP as a model stands for Contrastive Language Image Pre-training. CLIP is like the first multimodal model, like our case, it's vision and text, which tackles computer vision and was like released by OpenAI in 2021. It can be instructed in natural language to predict the most relevant text snippet given an image, and it does not need to be directly optimized for a particular dataset. It has zero-shot capabilities that are similar to the GPT-2 and GPT-3 model. So the way I'll be doing this is first I'll be talking about the task and then the architecture or methodology of the clip model. And then we will be talking about the results, the key takeaways, and the limitations. Finally, I'll be going through this amazing Kaggle notebook, which creates their own clip model and helps you train a model, train the clip model to get image captions for a particular prompt. So let's start. So the main problem that the clip model tried to address was that deep learning has revolutionized computer vision, as we all know. But there is one major problem with deep learning. A model that is SOTA on, let's say, a large data set such as ImageNet is good at one task and one task only. So let's say we have a great model that is being trained on images, such as a ResNet 101. So ResNet 101 on ImageNet has an accuracy or a top accuracy of 76.2%. But when we use ImageNet V2, which basically extends the test data set of the ImageNet with very representative pictures, but these pictures might have slightly different backgrounds or slightly different lighting, the accuracy falls to 64.3%. Now, as we go down the list, when we come across to ObjectNet, which is basically consists of all the classes of the ImageNet dataset, but these are presented in a different manner. For example, if we have the object of a chair, the chair might not always be in the same orientation or like in a similar orientation to the one seen in image. The chair may be overturned, or the chair might be in a background which the model has never seen before. The model's accuracy drops down to 32.6%. So the models that have been exclusively trained on ImageNet and are performing as SOTA on it, they are not very robust. they require significant effort to adapt to a new task. For example, you need to fine tune all the layers or a part of the layers of the model to get good results on these new data sets. So we needed a method that would be robust. But a brief, like if we like go through the results that Clip gave us on these data sets, we can see that the performance of Clip on the imaginary dataset is comparable to ResNet 1.1 of 76.2%. However, on ImageNet V2, it dropped a bit, but not as much as ResNet 1.1 to 70.1%. Whereas in ImageNet rendition, where the ResNet 1.1 dropped down to 37.7%, Clip gave us an accuracy of 88.9%. Similarly, we can see similar results in ObjectNet, ImageNet Sketch, and ImageNet Adversarial as well. So this is the problem that the paper is trying to address. So coming to our methodology, the first thing that I'd like to talk about is the data set that was created to train the model. So the data set consists of images and their text descriptions or caption, which are taken from Reddit. So this is done because when we try to create a traditional image dataset to train a model, it takes a lot of effort. We would need to gather the pictures and then label them one by one, which would take a lot of effort, and it is very difficult to create. But if we take images from Reddit that already have their captions, then that would help us get a huge dataset with minimal effort. So the dataset that Clip was trained on, it consists of 400 million images from Reddit. So another thing is that in most cases, in most of the datasets, the label that is, let's say in ImageNet, we would have labels such as banana, chair, bird. These are only treated as labels. We do not derive any context from them. For example, most of us would label encode these labels into forms like 0, 1, 2. And so we would be just training the model without taking any ideas of what this label could actually mean. For example, in a data set such as flowers 102 or GTSRB, we do not even have the labels. We just have numbers and a label dict that might tell us what each level would correspond to. So one of the many ways that the creators of Clip improved its robustness was through prompt engineering. Prompt engineering and assembling of these prompts helped us get a huge increase in the zero shot performance compared to like the baseline of using context class names. Prompt engineering and assembling boosted zero shot classification performance by almost 5 points on average of 30 standard data sets that the models were tested on. So yeah, so next we will be talking about how the prompt engineering was done. So when we use a class label without a context in the Clip and we do not use a prompt, we might face this problem of polysemy. So what's the problem of polysemy? Polysemy would be a problem where the same word could refer to two different things. For example, if we take the word crane, so the word crane could either be referring to the bird crane, or it could be referring to box crane, which is used to lift containers and things like that. Another example would be, let's say in the Oxford pets dataset, we use the word boxer. So in this case, the boxer refers to a breed of puppy. However, the model could think, as it's trained on natural language, it could think that boxer refers to the human boxers who fight. So that's why prompt engineering is very important in the case of training Clip. So another thing that would help us bridge the gap between a single word as a class and using a prompt was that we would try to create a prompt for objects that are often referred to in one word. For example, let's say you have an apple on a table and you want to classify that. So the prompt that we would use in this case is a photo of an apple. And this helps in improving the performance or the accuracy or zero shot accuracy of the Clip model on ImageNet by about 1.3%. So zero shot accuracy can also be increased significantly by customizing the prompt text from task to task. For example, a few of these would be let's say we have the Oxford Pets dataset again. We have a pet dog, and we would be stating that for this pet dog, would be a photo of, let's say the dog is a Labrador, a photo of a Labrador, a type of pet. Also, let's say in case of food, we would be specifying the type of specifying that the thing is a food. And let's say in case of an aircraft data set, we would be specifying that the thing that the photo is a type of aircraft. For example, let's say it's a propeller plane, so it would be a photo of a propeller plane, a type of aircraft. Also, there are data sets on which these ImageNet models have very low accuracy even after linear probing, and these data sets generally are satellite images and things like that. Clip also does not perform too well on these data sets, but after we do prompt engineering with the classes of these data sets, such as, let's say we have a satellite image of Delhi, then we would say a satellite image of Delhi, then Clip would at least be able to identify the thing as a satellite image, and be able to give us a better result than the linear probe or the zero shot models that are just trained on the image. Now, we will now talk about how the clip model actually works. So the first step in the creation of the clip model is contrasted pre-training. So the way clip model works, it's basically based on embeddings. So embeddings are basically, let's say we have a picture and we pass it through the model. Before we use like the classifier layers after the model, we get a fixed dimension embedding, which we can sometimes use for similarity tasks, or in more recent days on Kaggle, we often use them for arc face grouping. So like the main idea of clip is via these embeddings. So as you can see here we have a picture of a puppy, and here we have the prompt Pepper, the Aussie pup. The Pepper, the Aussie pup is passed through a text encoder, which would be like a transformer model, and the puppy would be passed through an image encoder, which could be something like a ResNet 50 or a ResNet 101 or even a vision transformer. And from here we get two embeddings. So the thing we want to do with these embeddings is we would want the prompts referring to similar objects, and let's say we have a prompt referring to a dog, and we also have an image of a dog which the prompt actually refers to. We would want these two embeddings to be closer. So the way we would do it is we want to measure the goodness or the badness of both our text encoder and image encoder. So a common way that we try to find out the goodness or the badness of two embeddings is via cosine similarity. Cosine similarity is basically a measure of how close two embeddings are in a particular vector space. So let's say let's say in this batch of images, let's say there are n images, n texts here, and there are n images here. So I1 is the image for prompt T1. So we want I1 T1, like the cosine similarity between embedding I1 and the cosine similarity embedding I1 and T1 to be large, but the similarity between embedding I1 and T2 or T3 to be small. Similarly, we want the similarity between I2 and T2 to be large, but the similarity between I2 and T5 or T7 to be small. So we want our model to increase the similarity between prompts and images that are referring to similar objects, and decrease the similarity between prompts and images that are referring to dissimilar objects. So that's how like we are particularly that's how the clip model is particularly trained. I will talk about this loss function in detail when we finally like go through the code, and then we will be able to understand how actually we are getting such a loss function, and how actually the model is optimizing both the text encoder and the image encoder at the same time. So like coming to the inference part, so let's say the way the clip model would work is that the clip model is already trained on 400 million images from the Reddit dataset. And now if you want to adapt it to like, let's say something like ImageNet or something like Flowers 101 dataset, then we would feed in the classes of the, let's say I'm taking ImageNet example, the 1,000 classes of ImageNet, and we'll create multiple prompts of the different classes. So here, as you can see, we have all the classes of the ImageNet dataset. we create prompts, and then we pass them through a text encoder. Through this, we get T1 to Tn, which is like n the 1,000 embeddings for like the 1,000 classes here. Finally, we take our picture here, we pass it through our image encoder, which gives us an embedding I1. Uh, and we would try to get the cosine similarity between this embedding I1 and the embeddings T1 to Tn. And finally, the two embeddings with the highest similarity, that would give us the prompt or the class of this particular image. So coming to the training part, the text encoder is basically a transformer text encoder. It has a base size of our 63 million parameters, and it is a 12-layer 512 tokens wide model with 8 attention heads. The transformer operates on lowercase byte pair encoding representation of text with a vocab size of 49,152. For computational efficiency, the max length of the input tokens that are fed into this model is limited to 76. So for the image encoder, we train a group of 6 models, so which are ResNet 50x4, ResNet 50x16, ResNet 50x64. So what the X part means is basically it's a ResNet 50 that's been trained with 4 times the compute for the original ResNet 50. And similarly, also we train the VIT based 32 patches, VIT based 16 patches, and VIT large 14 patches model. So as we need a matrix for the loss function of clip, we have to take a very large batch size of 32,768. The largest ResNet model, which is the ResNet 50x64, took 18 days to train on 592 V100 GPUs, which is really a huge number. However, the more efficient model, which is the Vision Transformer, took 12 days to train on 256 V100 GPUs. Also, we use the authors use mixed precision to accelerate training and save memory. To save additional memory, gradient checkpointing, which is a really awesome concept nowadays, and is being used widely on Kaggle as well, was used. And we also do half precision and atom training. The best VIT model, which was the VITL/14, was also trained on a larger image size of 336, which gives it similar performance to the fixed res model. So that's all about the training of the model. Next, we come to the results. So how are these results made? So we take a ResNet 50 and then we do linear probing with this model on all these data sets. So you might ask, what is linear probing? Linear probing would basically be like you take the ResNet 50 model, you remove the original classifier, and then under it you put a single linear layer that you would then fine tune on these data sets. So we could the clip has not been fine tuned on any of the data set. It is just as it is when it was trained on the Reddit data set. The only change that we did was, as I mentioned here, we would take the classes of the particular data set we are trying to train the model on, and then we would get all the embeddings for the prompts of all these classes. So we can see here, compared to the ResNet 50 model, the clip outperforms on the majority, like a good part of these data sets. On Stanford cars, it outperforms ResNet 50 by 28.9%. On Country 211, it's on 23.2%, and Oxford Pets 1.1%, Pascal BOC are 0.5%. However, it also does lose on a few certain tasks, such as 37.1%. So an observation that the authors made about the clip model was that it wasn't very good at the niche tasks. For example, it could not really identify faces in the celebs data set, or it could not really identify the gap between cars in certain other data sets. So it performs well on other general purpose data sets without any fine tuning. However, it fails to perform all that well in more niche data sets. Now, we would now continue with the key takeaways that we can see from the clip model. It is that clip is very efficient. Clip learns from unfiltered, highly varied, and highly noisy data. And the intent of the clip model was that it should be used in a zero shot manner, like the GPT-2 or GPT-3 models. Like we already know that the GPT-2 and GPT-3 models have like really good zero shot performance, right? So to reduce the needed compute, the authors also focused on certain ways that improve the training efficiency. The two algorithm choices that led to significant compute savings was that the first choice was using the contrastive objective for connecting text with images. In small and medium scale experiments, the authors found that contrastive objective used by Clip was 4 to 10 times more efficient at zero shot image classification. The second choice was the adoption of like the vision transformer, which, as we already seen, was much more efficient than the ResNet 101 or ResNet 50x4 or ResNet 50x64 models that were trained. So the models were originally trained in a image to caption manner, like the general way that caption generation is done, which is we take a model, we take an image model, and then we pass an image to it. We get the embedding. This embedding is then fed to a RNN, and then we try to get the caption. So originally, Clip was trained in this manner, but the results were not good, and thus the author switched to this contrastive method, which gives it 16% more accuracy on ImageNet after training on the same 400 million images. The second thing is that Clip is highly flexible and general because Clip learns a wide range of visual concepts directly from natural language. Clip models are significantly more flexible and general than existing ImageNet models. They are able to show significant improvements in zero shot performance on different tasks. To validate this, Clip zero shot performance has been tested on 30 different datasets, including tasks on fine-grained classification, geolocalization, and action recognition in videos, along with OCR. Although Clip's OCR performance is mixed, like it is not really able to accurately predict what the words are or what the number is, but its semantic performance in OCR is very good. So, like here you can see, as I mentioned before, the niche tasks is what Clip currently is weak at, but the more broader tasks Clip can do much better than a model that has not been trained on that task yet. So another important thing that could be mentioned is that the best Clip model, that is the one with the VIT L/14, outperforms the best publicly available ImageNet model at that time, which was the noisy student EfficientNet L2 on 20 of the 26 different transfer datasets that were tested. So it's not only outperformed the weaker models, but it also outperformed the SOTA model that was present at the time in 2021. Now, if we try to talk about the limitations of the Clip model, Clip is kind of very sensitive to the classes of a particular dataset that we feed to it. The manner in which these classes are designed can heavily influence both model performance and the model biases. An example that I'd like to take here is we find that given the label of the Fairface dataset, using the 39 race labels and a handful of egregious terms such as criminal, animal, etc., the model tends to classify images of people aged 0 to 20 in the egregious category at a rate of about 32.3%. But as soon as we include the label of child, the behavior drops to about 8.7%. So here we can see that just including one extra label of child shifts the model's classification of ages between 20 to 0 to 20 by about 24%. Additionally, Clip does not need task-specific training. However, we also, as we have mentioned multiple times before, on the niche tasks or like the abstract tasks, it does not really perform all that well. The example here is that when we use the celeb dataset and we only have 100 classes, Clip only has an accuracy of about 59.2%. However, when we move to about 1,000 celebs, the accuracy drops to about 43.3%. Although this is good for a non-absolutely fine-tuned dataset, a non-absolutely fine-tuned model, it is much less than the target-specific models that have been trained on these data sets. Another task would be poor generalization, which, as I mentioned before, Clip does not really perform well on images that it has not already seen in the 400 million images from Reddit. Although this subcategory is very less, the niche images, for example, images of specific car brands, or let's say images where you have to count the number of logs in a file, or satellite images where you have to identify whether a particular structure is a building, or like if it's a stadium or things like that, things that Clip has not seen all that often. Clip would have poor generalization or poor performance on that. So that would bring me to the end of the presentation, and now I'd like to go forward with a code demo. So the first piece of code that I would like to go through would be the official interacting with Clip notebook that OpenAI provides. So like it's like freely available on the GitHub of Clip by OpenAI. So the way it's working is currently, as I mentioned, Clip would have two parts. One is the text encoder, and the second part is an image encoder. So the currently available models that are in vision models in Clip are Resonant 50, Resonant 101, and the Resonant 50X4, along with the VIT large models, and also the SOTA VIT large, which is trained on the 336 cross 336 image size. So here we are using the VIT base with 32 patches, and we try to we try to load in the model. So like here is the it comes with a pre-processing function of its own, and we can see that clip.tokenize would like tokenize it into like 76 tokens, as we mentioned, because the size has been limited to about 76 tokens. So here we are using images from the sk image package, and these are the prompts that we already have, and uh, here we are just just display the images that are present. So we take all the images that we have and we stack them up, and then we are trying to tokenize all the prompts. Like here we can see that we are trying to create the prompt. So this is this is the description from text, and here that is how we are getting the particular prompts. And with torch.nograd, we will tokenize and get the embeddings for the embeddings of the image features for all the images and the text. And here we can see that we are normalizing all the embeddings, and we thus get the similarity. So the similarity is getting it's done by getting a dot product between the features of between the features of the text and the transpose of the image feature. And so when we try to plot the similarities, we can see that the highest similarities occur in the correct places. So the model is correctly predicting all the classes that all the prompts for a particular class. And so like here you can see that a cup of coffee or a saucer is assigned to the correct image, and that's the highest one that we have. Also a person looking at a camera on tripod, that too. And if we come here, portrait of an astronaut with an American flag, that's the correct one as well. So here you could see that the clip model performs exceptionally well on assigning the correct label to the correct image, although these images are not the part of the 400 million images that it has already been trained on. And so here we are testament of the zero shot capabilities of the clip model. Next, we would like you could focus on the zero shot image classification on the CFAR 100 dataset. So what this would tell you is that, as I mentioned, that to adapt the clip model to a particular dataset, we would take the labels for the classes of a particular dataset, and we would generate prompts, and then these prompts are tokenized and normalized as well. Then we would take the image features and get the similarity, and finally we can see that let's say it says a cup, so this is a cup. It would here the main probabilities are man, or if we go to the top two, then it would be a boy. And here this is a picture of a rocket, so it's been like pretty highly confidently said that this is a rocket. Similarly for the motorcycle, that's what it has been done. Yeah. That's how the clip model is trying to that's how it has been adapted to a data set that it has never been trained on for test out its zero shot capabilities. And now we would go on to this amazing notebook by go on to this amazing notebook by Moin Shariatnia. And this the main objective of this notebook is given a query, you would want the images that are refer to that query the most. For example, here we are trying to get the top 9 images for a particular query. So this notebook also contains like a very good breakdown of the clip model, and it also explains to us how the particular loss function has been made. Because as you remember, the loss function in this does not really depend on the logics; it depends on the matrix that was formed, like the matrix that was formed from the embeddings of the text and the images. So moving on. This is we just load in the captions that we have and pre-process it a bit. So the images are from the Flickr 30K dataset. And coming to our dataset, so the main things that we pass through our dataset are basically the captions and the encoded captions, and then we have the images. And so the images are resized, and then they are conformed to RGB. And as we use class first in PyTorch, we permute them to 201. And this entire notebook is based on the TensorFlow implementation or Keras implementation of Clip. These are the transforms. So now we come to the image encoder. So the image encoder is nothing special. It's basically the image model. In this case, it's a resonance 50. And using this resonance 50, we get an embedding of size 2048. Next, we come to the text encoder. So the text encoder that's used here is the Distilbert. Like Distilbert is pretty much as good as BERT, but it's a lot lighter and easier to train. So the embedding, another important to mention is the embedding dimension is 768. Now, one thing that we have must noticed about the clip model is that both embeddings need to be of the same dimension. But in this case, we have the image embedding as 2048, but the text embedding as 768. That is why we need a projection head. So what the projection head is basically doing is it's bringing the 2048 embedding to a dimension of 256, and also it's bringing the 768 embedding to a dimension of 256. That way we can multiply, we can get the dot product of both the embedding matrices of the image embeddings or the text embeddings. So it's basically like a linear layer which brings down the dimensionality of the which brings down the number of which brings down the dimensionality of the text embedding to the required 256 dimension and the image embedding to the required 256 dimension. So it's basically that, and here we have the projection layer, which from which we get the correct dimension. This is passed through a ReLU layer, which is like the activation function, it's an improved version of ReLU. And then we have another fully connected layer, which is then passed through it is then summed up with the original projected one, and then it is passed through the layer normalization, and which we then return. So finally, we will try to build the clip model. So the first thing that we need are basically would be obviously the image encoder as well as the text encoder. Then we have the image projection head. So this would project the image embedding to a required dimension, and the text projection head, which would project the text embedding to required dimension. And then that's what is being done. So the forward part basically gives us an intro to the loss function that we are particularly using here. So firstly, we get the image embeddings and the text embeddings. Next, we will try to get the logic. So why would this be like a logic of the image embedding or text embedding? So the way it would work is that, let's say you have a batch size of 4 and a dimension of 256, and you have embeddings that refer to that are of this particular dimension. So the dimension would be 4 cross 256. So for the logics, you would want that the logic for since all the embedding values in this matrix are between 0 and 1, you would want the value for non-similar text and image to be as close to 0, and you would want the value for a similar text and image to be as close to 1. So after you get the dot product, so cosine between two vectors is basically the dot product of these two vectors, and then you pass it through the softmax function, which would be basically the e to the power of the particular dimension to the particular element divided by the sum of the exponents of all the particular elements, all the elements in that particular dimension. After we pass it through the, after we pass this matrix that we get after the dot product through this softmax, we get this matrix which basically gives us our logics. So here you can see, as we have previously seen in the presentation, that the diagonal columns, diagonal elements in the matrix are the ones that refer to similar embeddings and similar objects, similar images and similar objects. So we want these as zeros, and we want everything with these as ones, and we want everything else as zeros. So coming back to this, so that's why we get our logics as text embeddings. We are getting our logics, which is the predictions. We would get these as text embeddings multiplied by image embedding transpose divided by self temp dot temperature. So, and then we try to get the image similarity. So the image similarity would be image embeddings multiplied by image embedding transpose, and the text similarity, that is the similarity between texts, as text embeddings at the rate text embeddings transpose. Finally, we sum these two, image similarity plus text similarity, and then we take the softmax of the entire thing to get the targets. And finally, the loss that we try to calculate in this is basically the cross entropy loss, because right now it would basically be like cross entropy loss, because we have the labels as zeros and ones, and we have values between 0 and 1, and we would want the right values to be as close to 1 and the left and the wrong values to be as close to 0. That is why we are using cross entropy loss here. So the text loss would be logics with targets 1, and image loss is similarly cross entropy, which is logic transpose and target transpose. And it's the entire loss is basically a mean of both these losses. Now coming to the train part. So the train part, this is basically a very simple training loop. We take all the prompts or all the captions of the particular images, and we create a train data frame as well as a valid data frame. Then we try to create the PyTorch dataset followed by the data loader, and then the training loop would basically have the model basically be a forward pass followed by the usual things that we see in a training loop, followed by the validation loop, which is pretty similar to what we have seen so far. And in the main part, we basically define everything that we needed, and we train our model. Finally, when we try to inference the model, we would try to get the image embeddings of all the images that we have, because the task we're performing here is the opposite of what the clip was designed to do. So the way the original intention of the use of clip was to pass in image and then we would get the correct caption, but here we are passing in the caption and we are getting the top 9 images for that particular caption. So the way the task is performed is similar, just that the final objective of the task is different. And here we get all the image embeddings, and then basically we would get the top 9 features. So the way this is done is basically the same way the clip model actually worked while training. We get the text features from the text encoder, then we project it to the appropriate dimension. Finally, we will normalize both the image embeddings and the text embeddings. Then we get the dot product, that is the similarity, and then we get the top k values for that particular query. And finally, we have all the image file names which we get from the index, and we plot our model. So if we pass in a query, a dog sitting on a grass, you would get all these images which are basically of a dog sitting on a grass. So here, so this was like a demo of how the clip model was made and like the loss function and how it was trained. So hopefully you liked it. So that kind of brings me to the end of what I had to say about the clip model.
So thanks, Aishik, for the presentation. Like I hope the presentation was useful for the community members. Like a few of the questions that we have received from the community members prior to this live event was majorly like a lot of the students have started working around clip model in their projects, right, in their self projects and all those things. And when they go for internships or like let's say full-time opportunities, what type of questions they can expect, or how should they portray their clip model based projects moving ahead in the interviews, or like any experience you might have around that?
I am part of this club in our IIT called IT.ai. So last year we had this project on the clip model, and it was basically entire pipeline where the user passes in a prompt for a type of dress that they want, and we had a GAN after the clip model which gave it a dress, and the GAN was used to superimpose the dress on a particular model on the particular person that the dress was intended for. So according to my experience from the interviews that I have given for the internships or the placement interviews. So the questions that are asked with regards to ML model would basically be basic questions. So you would need to know what the architecture is. Not really delve deep into the architecture, but have a basic idea so that the interviewer would think that you have done work on this. For example, if you are talking about the clip model, you should know that there's a text encoder, there's an image encoder, and we use embedding similarity for this. And let's say if the loss function in clip model is the very innovative part, as we are using contrastive learning here. So that is something that I found while reading the paper is like the most important part of the paper, in my
Mhm.
opinion. So that is something that if I was in part of interview, like that is something I would expect to be asked in an interview if the interviewer decides to focus on my projects.
Got it, got it. So that well summarizes how should we approach and how should we answer those kind of questions. And one another thing is like when we are talking about clip model and like we also we also saw the architecture and all those things in the talk today. So like a student have their question right around like if they want to get this clip model used in their projects, what would be your most uh, favorable suggestion for that student to kickstart with utilizing clip model so that they can get started and can at least make a project out of it?
Okay, so the clip model, as we already saw in the notebook
Mhm.
provided by OpenAI, so all the models are freely available for anyone to use. Like
Mhm.
you get the text encoder and the image encoder as well. You would not need to design it by your own to like train the clip model. Yes, you would not be able to repurpose the clip model all that well on like a very niche data set, as you would not have the compute to train like a very large model like a VITL/14 at the size 338 would be impossible for you to train on the resources that you currently have access to. But you can use these pre-trained models to create a particular project. Like as you saw in the second notebook, I displayed that uh, we used Distilbert and just Resonant 50, and that gave us pretty good results as well. So if we want to completely repurpose the model, you could try something like that, like carry over the conception of the clip model, but scale it down to your own compute resources.
Got it. So it's like majorly how you align with the resources that you have and
Yeah.
align with the knowledge that you
It
have
mainly
around it.
depends on what kind of objective that you have. So if like according student project, all you need is like a proof of concept. No one would expect you to be SOTA on a particular data set because that would require resources that you currently do not have.
Yeah, yeah, got it. And like coming to like another student oriented question, it's like a lot of the models have been coming up in the recent days, and like it's a lot to cover up in a little less time, right? Like you have these much of models coming up and these much of architectures which you need to read about. So how do you get updated with these new advancements in the research that's going on, or what would be your suggestion to them so that they can also at least get started and get a better understanding? Like, though I know it's a tricky question to be answered, because like it again is a trade-off between your time and the domain in which you are working, but still
Yeah.
your preference around that.
Okay. So one thing that I have done in like the past is that I am kind of pretty active on Kaggle. Like I haven't been for like the past 2 months, but before that I was pretty active on Kaggle. So in the Kaggle competitions, there are people like, for example, someone that I religiously follow on Kaggle is Chris Dior. So there was this competition on popularity, and like 2 days before the competition ended, Chris Dior published a notebook. Chris Dior, 2 days before the competition ended, Conv Next was released, and it was the new SOTA on ImageNet, right? So Crit Diot used Conv to get his solution to of the pet popularity challenge. So and then 2 days later, when the competition ended, he published the notebook. So that way, I got to know of Conv. And even before we had this competition called Chai. So Chai was the first time that I personally widely use the Deberta V3 large model, which is currently like everyone. Deberta is like the new Roberta. So that is how I have been keeping up with it. Another way that I keep up with all the research that's being done is you can use LinkedIn, where there's this a person called Aman who posts blogs on particular interesting research, or you have Lillog, which is a great place for blogs on the new research that is coming up. Like she has an extremely good article on diffusion models. So I use blogs and other people's work because I personally do not have the time to go through every piece of new research that comes through. So I need someone to like make a gist of it because I do not have the time for it.
Yeah, yeah, got it. And how has been your experience around diffusion models that's been coming up? And like, if anyone wants to get started, maybe any resource that you have on top of mind, though that's that's tough to answer at this point of time. But if you have any exposure to diffusion models and how it has been, and any suggestions for the audience.
So, yeah, I personally haven't used diffusion model other than like the OpenAI API that everyone uses to create those
Hmm.
amazing pictures. Other than that, as I mentioned, there's this amazing article on diffusion models at Lillian's blog. Like it goes by, it's a GitHub blog, and it's by Lillian Wang. So you could visit Lillian Wang's blog to like get a uh, good overview of like the new research that has been coming up. Yeah, like I
Yeah.
could like I would share the link with Ion, and if you could share it with the community, that would be great
Yes.
because,
Yes. Sure. Sure. Sure.
in my opinion,
Uh,
it's like a great blog for people to know.
Yeah. So like we have another question around, if would the presentation and the notebook be shared? So definitely, like Aishik will share that with me, and I can definitely put it on the community's channels for the community members like knowledge, in case they have missed joining this live or they would want to refer to this at a later point of time. So like coming to the last part of this session, it's some of the students who have been facing interviews recently, like they were asked questions around clip model architecture and all those things, that's not the majority of the interviews, but in case if they want to answer, would you like, what would be your suggestion? Try directly going into the mathematical equations or all those things, or take up a use case and then trying to understand with the help of clip model that how the things are, and all those things become easier during your interview when you try to pick up a use case and then try to see how the model works, and then give a explanation to them rather than going only to the maths and technicalities of the things. So
Yeah, like
what would be your suggestion?
I would recommend taking up a use case because that makes it easier for you to explain it to the interviewer. Because
Mhm.
going directly into the mathematics would be very abstract, and the interviewer might not be able to relate to like what is the particular use case of the clip model in the project that you have done. So if you just
Mhm.
take up an example and then go into the mathematics or talk about like the core features of the particular model, it would be better, because like similarly in the OpenAI blog, they do not directly talk about the loss function at first. They would first give you an abstract overview of how the entire thing is working, that you get to know that entire thing works on a matrix, and then they go into the inner workings of loss function. So that, like when I read it, that made it easier for me to understand. And
Mhm.
the main objective during an interview would be to make your interviewer understand as well. So I
Mm.
would say making it going through examples is a better way.
Yes, got it, got it. So thank you, Aishik, for coming on this event virtually, though. So looking forward to more talks and more awesome work from you. The community wishes you all the best for your future endeavors and in the data science journey. So thanks for your time to all of you, and thanks, Aishik, for the resources and for taking up his time to help us understand more about Clip Model. Thank you all.
Thank you.